Okay, electricity 2. To do this, you need to have seen the first video on using the oscilloscope. So now, we need to discuss peak and RMS voltages for alternating current supplies. So, I've got here, normally, if you want to take a mean of something, it's a kind of, let's say, it's an okay way of describing something that's changing. So if I was going to say, okay, it's an okay way of describing something that is changing. So I thought about that and thought, okay, in what kind of situation is a mean a kind of okay way of describing something? Well, let's say I've got a kind of oscilloscope trace here. I've got voltage and I've got time. And I said to you, okay, this voltage is kind of, if I was going to take a mean of that, I might discover that it's basically always plus 3 volts. So on, say, my positive voltage and my sort of negative voltage scale, for this time interval, whatever it may be, it's always about plus 3 volts. So that's fine. I could kind of average that, and I get that it's plus 3. However, what if the number's not quite so convenient? So for alternating voltages that we generally call alternating current, AC, a basic mean often doesn't work, and I'll explain why. Okay, it just won't work. If we have a proper conventional display from an oscilloscope and so I had one that was more like in a conventional pattern like this, you might think, oh, all right, okay. Now clearly that would simply, if you take the mean there is 0. So if I say, oh yeah, I'm going to sort of average that or take the mean to be more mathematically precise, I'm going to get 0 volts. But actually, I've got a useful electrical signal there that could actually be a useful power supply. That could power lamps, it could power heaters, it could power all sorts of things where the direction of the current is not important. So clearly, this taking a simple mean is not helpful. And I need to think about doing something else. So the basic way that the physics community have sorted this kind of thing out is to say, okay, before we take a mean, we'll square it. So we take the square of the voltage function. So what would happen to this is, you'd be going along this top curve and you'd be sort of taking a sample at every tiny little interval that you wanted to and measuring off the voltage for each one and squaring it to get the function on this side. So let's say, for example, at this point, however many thousandths of a second in, I've got a voltage of -2. Now when I square -2, I get -2 times -2 is +4. So what happens is, the bottom halves get, the squaring makes these lumps sort of steeper. So it makes the crest steeper and the troughs become positive. So I would have an initial trough that would be matching this part. Then I'd have this next trough which would be matching that part. Then this trough would again become taller and it would go positive because I'd be doing things like -2 times -2 is +4. I'd have like -3 times -3 is +9. So it's going to go higher up the voltage scale, and I don't have any negative regions. Okay, now, and I kind of started off here to make that look right, so I'm just going to do a bit on the other side to just, because of course this part would also go positive and taller, and this would go positive and taller, and I get my squared function, which looks something like that. Okay, now So to describe this alternating voltage, I could consider taking the mean of this. Okay, so we can take a mean of this squared value, and that would be something useful. In this case, I don't know, if I'm suggesting that that's 9 and some of these others, it might be, say, +6 or +5. So that's the next step. I take a mean. Now, okay, so this mean is of the squared. So it's too big. So our general method is we use a thing called the root mean squared voltage. Okay, so the root mean squared voltage, this is a fairly straightforward concept. We're going to take the graph from before, just like this, and we've got our nice tall peaks of the squared voltage function, like this. We're going to average it, and then it will be too big. So if I decided to average that and I got a value down here, it's too big. So I would find this value. Now if I'm saying that's about 9, this is about 6, so let's say this is about 5 volts. I would then, to find the root mean squared voltage, would be the square root of the 5. Okay, now you don't really ever do this. You're just going to go between values in a method I'll show you in a second. But that's what I'd be trying to do, and as I can't remember the square root of 5, I will just look it up. And we'll say that that's 2.2 volts. So going back to my first function, where I was kind of saying, well, these peaks are at about 3 volts, and I've worked out some values and I've decided to square it, so now I get peaks that are at 9 volts, 3 squared, and now I've taken a mean of that, which I've estimated to be about 5, and then I've taken this, and that's kind of where I end up. So this is a root mean squared voltage. I've explained the story of how we get to it, but really you don't need to worry too much about the story. Okay. The root mean squared voltage is actually very important because if you have a direct current supply, so let's say I had a direct current supply that was 6 volts, which looks kind of this, and at the same time I had an alternating current supply that was bigger, then if the root mean squared value for this was 6 volts, voltage time, trying to be tired of my graph work, then let's have a look at the circuits for this. The root mean squared is equivalent to the DC value that would have the same heating or lighting effect. So this is the important point here. That these two circuits are equivalent in that if I had an alternating current supply, which has an RMS voltage of 6 volts, then, and I had lamps which were identical in both circuits, then we would find that my 6 volt RMS and my 6 volt direct current, you would not be able to tell the difference between these lamps. These lamps would be super equal brightness because that's what the RMS voltage is equivalent to the direct current voltage, and it allows us to make alternating current circuits that do the same job, exactly the same job as a direct current circuit. And we can chop and change between the two. So, and the way you do that is you go that basically the peak voltage equals root 2 times the RMS voltage. So if I want to go back here and say, okay, if the RMS voltage for this alternating current was 6 volts, then what will the peak voltage be? Well, I can just use my equation for that. That's pretty straightforward. If I do square root of 2 times 6, and then remember the square root of 2 is roughly 1.41, but I'd be using that on my calculator to avoid any confusion. If I multiply by 6, I'd get 8.48. So I'd be looking at basically 8.5 volts. And this is the simple way you go from V peak to VRMS. And obviously, if you want to go the other way, the fact for you algebra fans out there, if you want to go the other way, you're going to have to just bring the root 2 down to this side. So if you want to do some of the prep questions and say, okay, I need to find the RMS voltage and I know the peak, you take the V peak and you just divide it by the square root of 2. Okay, so that's a fairly long story because the maths for this is pretty simple. Okay, but I've tried to take a bit of time explaining where it comes from. Okay, now you can do the worksheet questions on various waves, looking at oscilloscope traces, which look like waves, finding the period and the frequency from the first lesson, and also looking at the peak and RMS voltage from the second section.